liver is to make bile. And bile is not a digestive enzyme, but it is an emulsifier. It emulsifies the fat so that we can absorb the fat directly through the intestinal wall. And actually we absorb it directly into the lacteals, the little lymphatic vessels that extend up into the villi, right? Let me tell you why that is named lacteals. We used to, every time we would operate on people, most all of the time that person had been in the hospital or at least had been NPO, nothing to eat, since midnight the night before. And so they did not have any food in their stomach and a bunch of food in their intestine. But occasionally we would operate on people that had come in from a car accident, for example, and maybe they had stopped at McDonald's an hour before. And so they had lots of food in their stomach and in their intestine. And when you looked at their small bowel, you just lifted it up and looked at it, you can see in the mesentery all of these white, stringy looking vessels. And those are actually lymphatic vessels that you can see, and they're full of white fat, droplets of fat, absorbed directly through the wall of the bowel. We call them lacteals. Lacteal refers to lactation, refers to milk, because it looks like milk. It's not, it's fat. Okay? Going back to the anatomy of the bile system, the common bile duct is formed by the junction of the cystic duct and the common hepatic duct, and it passes within the lesser omentum towards the stomach, where it goes through the wall of the duodenum, and it meets up there. It meets up with the pancreatic duct right at the duodenal ampulla, and then empties into the duodenum right there. So here it is coming in. Here's the cystic duct coming from the gallbladder. This is the common bile duct. It goes behind the duodenum, comes down this way, and meets up with the main pancreatic duct just before they go out and empty into the duodenum. Now remember, these are both alkaline solutions that are coming in order to neutralize all the acid that's coming out of the stomach into the duodenum. We want to neutralize it, so from here on down it can be it's a neutral, it's not so acid. That's the way it works. Notice here's the hepatic portal vein, which is that great big vein that's collecting the blood from all of the intestines, heading to the liver. Here's the common hepatic artery, heading up there as well. And we oftentimes refer to this as the portal triad. There's portal triads in the liver themselves, but this is a portal triad as well, and it involves the common hepatic artery off of the celiac trunk, the hepatic portal vein, which is this vein that's formed from all these veins from the small bowel and colon and stomach mesenteries, and the bile duct, which is obviously bringing stuff down this way. Okay, this is the business of the common channel, where the two of them come together right as they empty out into the wall of the duodenum. This is just a real super close-up of this. The thing that's important that you understand is this is why gallstones can cause you terrible problems with your pancreas. If you get a gallstone and it passes out of your gallbladder and it passes down your bile duct and it gets stuck right here, for example, then that's not only going to back up your bile and make you turn jaundiced and yellow, but it's also going to back up your pancreatic duct, and that is a very bad deal. That's why people get really, really sick from pancreatic juice, because we've already said that if pancreatic juice gets activated, it's going to digest your pancreas. So this is the reason that people with gallstones get pancreatitis, is because this is a common channel right here, and when a stone comes down from the bile duct, it blocks off both of them. The physiology of the liver, metabolic regulation, hematologic regulation, and bile production. So it really does a bunch of things for us. It's really the kind of like the metabolic factory of your body. It makes lots of the proteins that are in your body, all of your albumins and globulins and blood clotting factors and all that stuff. It also regulates your blood by eating up blood cells if they're old and dying, although they're also eaten up by the spleen. and it also produces bile, like we talked about. The thing I want you to remember is that bile is not an enzyme. It's just an emulsifier that makes the fat break up into little bitty globules so that we can work on them. So that the digestive enzymes that are released by the pancreas, for example, the lipases, can attack those little micro droplets of fat and get them broken down so we can absorb them. So, liver regulates the composition of your circulating blood, your nutrient metabolism. It stores glycogen. Remember the old concept of carbo loading? Most of your glycogen is stored either in your liver or in your muscles. That was one thing we thought worked well with carbo loading, but it really didn't work. We store a lot of stuff in the liver, like that glycogen. Liver also serves to deactivate some drugs. And think about not having a liver. If you go into liver failure, you can't do any of this stuff, and these people just literally fall apart. They can't clot their blood. They can't eat any proteins because they can't break them down. They can't beat fats very much because if they're not making enough bile, their fat just kind of goes right through them and comes out in their stool. They don't have a place to do this. They can't inactivate any drugs. I mean, your liver is super important to you. And people that are in liver failure, you will meet some in your life. They are absolutely, to me, pitiful. They're just pitiful because there's nothing that we can do for them without giving them a new liver. Usually, the reason they lost their liver the first time around was because of alcohol and cirrhosis. That's the most common cause of liver failure. The second one is hepatitis and hepatitis C, which are other causes of loss of your liver. But if you put a new liver in there, they're probably going to catch the same thing again. So it's kind of a tough deal. So all this blood that comes past the intestines, enters into the hepatic portal system, flows to the liver, as we've talked about. The liver cells extract the stuff they want out of the blood, and they put wastes and stuff back in the blood. And they're going to eventually you're going to percolate through the liver, get in there to that central vein. The central vein is going to merge with a bunch of other veins to form the hepatic veins. Now remember, that's why I tell you got to be really careful about your naming. Hepatic veins and hepatic portal veins are completely different. They're on opposite sides of the liver, basically. Hepatic veins are leaving the liver and going straight into the vena cava and back to the heart. Hepatic portal veins are coming from the intestines and going to the liver. Okay, so be careful when you name those when you think about that. I think we've said enough here. What are some of the metabolic activities of the liver? Well, it breaks down carbohydrates. So that blood that just came from the intestine that's all full of sugars, that sugar can now be metabolized and you can start breaking it down even further, and the Krebs cycle can start working on it. You can start manufacturing ATP. The liver is going to help you break down the blood as it goes through the liver. The fats are going to get broken down. The amino acids are going to get broken down. Some waste products are going to be removed. Vitamin storage takes place in your liver, and drug inactivation, like I mentioned. Also remember that the liver is your largest blood reservoir in the body. It also takes a huge amount of blood, about 25% of your cardiac output. So 1 cc out of every 4 that your heart pumps is going to your liver. Quite a lot. How does it control your blood, your hematology? It eats up things that come through there that it doesn't want to keep anymore. It synthesizes all those plasma proteins like the albumins, the globulins, and the blood clotting factors. It breaks down a lot of your hormones after they've seen their day. It removes a lot of antibodies that you don't need them anymore. If you've fought off this infection or that infection, then it'll eat them up and get rid of them. It can help with toxins, as I mentioned, and it also synthesizes bile. What are the functions of bile? Well, just remember that lipids, dietary lipids, the fats that we eat, are not water soluble. They're just like that bottle of vinegar and oil that's on the table. They don't dissolve in the water, therefore you really can't absorb them as they are. Mechanical processing in the stomach, as the food churns in your stomach, it starts to break those big globs of fat, like that piece of meat that had a piece of fat hanging on it from that steak you ate last night. That thing has to be broken down, and it starts up here in the stomach, and it creates these large fat droplets. But then it needs the bile that mixes in down here in the duodenum to further break those droplets apart and really emulsify the fat. So now it's in tiny, tiny little droplets. That increases the surface area, allows the lipases that are there to really get at the fats and break it down and eat it up. That's really the function of bile salts. Pancreatic lipase is one of the enzymes released by the pancreas, obviously, and all it can do is work on those little tiny micro droplets. It can't go attack into the center of them. It can only come from the outside, and so they've got to be emulsified into little tiny droplets so that these things can work. Otherwise, the fat passes on through you, and that's not a good deal. There's a little piece of trivia here. The way you know that you're not absorbing your fat properly, and I bet this has probably never happened to any of you in the room, is that your stools float. Your stools will float. And when you see patients that their stools float, it's probably because their stool still has a lot of fat in it, which makes it float, and that's not good. It means they're eating this food and eating these fats, and they're just passing right through them. Make sense? Let's talk about the gallbladder for just a minute. I think I kind of talked about this yesterday. It lives right here in the right upper quadrant on that fossa on the posterior surface of the liver. It has three parts. This is silly, don't learn these. Fundus, body, and the neck. The cystic duct is the duct that leads from the gallbladder, and it's going to hook up with the common hepatic duct, and when it does, it's going to form the common bile duct. I drew a little diagram for you the other day going over these things. So what does the gallbladder really do for you? Well, it stores your bile. Do you really need to store your bile? No, because people do perfectly fine without a gallbladder. If you don't have a gallbladder, it just means that your bile dribbles into your duodenum all day long. But we make so much more bile than we really need that that's okay. Now the way it should work is that the little valve going into the duodenum down there closes off between meals, and the bile can't get into the duodenum there for a while, and it backs up into the gallbladder, and the gallbladder fills. It can fill, I want to say, about 150 cc's or so. The problem is that as long as that bile sits there in the gallbladder, it's not flowing or doing anything. It's just sitting there, and depending on your level of cholesterol in your bloodstream, it can crystallize out, and that's what forms gallstones and causes these problems. Now, if this is the normal situation, you eat a meal, food churns in your stomach, starts being dumped out into your duodenum, and the wall of your duodenum secretes this hormone that we've talked about a little bit. We'll talk about it more now, called CCK, cholecystokinin. And basically, cholecystokinin says to the gallbladder, hey, Mr. Gallbladder, we've got a bunch of fat down here in the duodenum. We need some bile to mix with it, right? To emulsify the fat. And so what happens then is that the duodenal papillae opens up, the gallbladder squeezes down, it pushes the bile on down into the duodenum to mix with the food. But like I said, it doesn't really matter. It does just fine if it dribbles in all day long. it says a full gallbladder contains 50 to 40 to 70. I know it does. It holds more than that. I've seen it. But the bile, as it sits there in the gallbladder, not only does it just sit there and things can crystal out, but it also concentrates it. It reabsorbs a lot of the water back out. So the bile may have looked light pale green when it went in there, but after it sits in there for 2 or 3 hours, it looks dark black because it gets really concentrated. So the composition of the bile changes, the water is absorbed, and everything becomes more concentrated. And that's why stones form, is because they do get concentrated. Yeah?
The CCK,
Yeah.
does that get triggered when there's a lot of fat in the duodenum, or does it get triggered no matter what is
Well,
in
when
it?
there's food in the duodenum, it gets triggered, but a big fatty meal will trigger it a lot more.
Okay.
That's why when I was telling you the story about the lady who got a gallbladder attack with the pain in her back, it almost always follows a fatty meal. So pizza's the best choice.
Put me in the hospital.
Yeah, it'll put you in the hospital. So anyway, I think we've talked enough about this and these glands and so forth. Let's move along. Remember that the GI tract pretty much just runs itself. It doesn't need a lot of nervous innervation. We know that the parasympathetic system will stimulate the gut and it'll make it work faster. And if you're looking at the tiger and you're fight or flighting, your GI tract is pretty much going to go to sleep. And that's why, as I think I told you before, you don't want to eat or drink while you're running a marathon, because that food and water is just going to sit there in your stomach and bounce around, and pretty soon you're going to be stopping by the side of the road and vomiting just to get rid of it, because it doesn't go downstream, because you do not digest while you're fighting and flighting, while you're running. Okay? We had these other reflexes that we talked about after a big meal usually. That's really nice. There are neurons that do synapse in the digestive tract. And remember, they live between the layers of the muscle, and it's called the myenteric plexus. Not really all that important, but yet it can give you big-time diarrhea if you get nervous enough, I guess. We've talked about all these hormones. I think all the ones that I really want you to know about already. Let's just kind of run through this list and make sure we have covered them all. The big ones that you need to understand, you need to know where they're made and what they do and what their target organ is. Secretin. Secretin is made in the duodenum, from the wall of the duodenum. The secretin goes and stimulates your pancreas to secrete, and mainly it stimulates it to secrete an alkaline,
Bicarbonate.
lots of bicarb, right? Bicarbonate is your base. Cholecystokinin is also made from the wall of the duodenum, and it stimulates the gallbladder to empty. Let me skip down here to gastrin. We've talked a lot about gastrin. Gastrin is made in the wall of the stomach, and mainly it's formed when the stomach swells, and gastrin does just what it sort of says it does. It makes the stomach secrete acid and pepsinogen and all that stuff to really make the stomach work and get the digestion going. We have a couple of others that I don't really hold you to. GIP is gastric inhibitory peptide. It's on those diagrams that we went over with the other day. It does just what it says. It inhibits the stomach. So it's kind of the opposite of gastrin. Vasoactive intestinal peptide is a thing that sends more blood to the bowel. Once again, I wouldn't worry much about it. Enterocrinin, I don't know what it does. Yeah?
I can't remember what it's called. It's something like sinusoid,
Sinusoids.
that like reverses the gas, or it's kind of like the anti-gastrin. What is it?
Sinusoid.
Yeah, somatostatin.
Somatostatin?
Okay, yeah. So is that a hormone?
Yes.
It is.
It comes from the pancreas. Remember?
Okay.
Let me go through this because I think it's on this list here. It's
Okay.
coming up. Secretin we've talked about. Cholecystokinin we've talked about. This is just kind of a nice review for you, and it's in your PowerPoints if you look at them. GIP, gastroinhibited. It's mainly secreted when fats and carbohydrates enter the small intestine, and that's so that your bowels will slow down. Fat, if you eat a real fatty meal, it wants to run right on through you because the fat is kind of irritating the inside of your gut. And so you need this gastric inhibitory peptide to kind of slow things down so that you can take time to absorb all your fats. You got to understand that our body wants to absorb every single calorie that you take in your mouth. And it does. Our bodies are so good, they let nothing go out in your stool. You shouldn't lose any molecules of fat, any of carbohydrate, or any of protein. Nothing should pass right through the system. The system is so good that with all of these things we're learning about here, we get everything out of whatever we eat. Now that's kind of a problem to some of us because we'd like to just be able to pour it down the toilet, but it doesn't work that way. We absorb every molecule of all that stuff. VIP makes these intestinal glands secrete more. And it also starts to inhibit the acid production. VIP is not released until the food starts leaving the stomach and going down the bowel. But let's just leave it at that. Gastrin, we've talked about at length. Enterocrinin is this one that I told you I didn't know anything about. It's released when the chyme enters the small intestine. Okay. It stimulates mucin secretion by the submucosal glands. Well, duh. You dump a bunch of stuff into the duodenum. Brunner's glands get activated. It starts making all this mucus to protect the duodenum. This is a nice little review slide that I hope you'll all take a few minutes to look over. And basically, it talks about, it doesn't talk about the cephalic phase of gastric digestion, right? The cephalic phase is when you're thinking about the food, you're smelling it, and so forth. And all those messages come down through your vagus nerve to stimulate the stomach to start making acid, even before you've eaten a bite of food. Anyway, gastrin and GIP and secretin and CCK and VIP, there they all are. I think the most important ones for you guys is gastrin, secretin, CCK. This tells you what they do. All of these things are leading to one thing, and that's to help us absorb all the nutrients out of our food. Another little summary slide. Let's talk about the overall picture a little bit more. It takes us about 5 hours to digest a meal. Okay, we take it in. It sits there in our stomach for about 1.5 hours to 2 hours, just churning up and starting to mix with the enzymes that are in your stomach. Then it starts very gradually being passed off into your small intestine. There's a lot of movements of that occur in the mucosa. Think about this. The inside of your small intestine has lots of surface area, right? And so here's a couple of villi, and as the food is coming down through the lumen of your small bowel, there's little chemicals and carbohydrates and proteins that are all laying right there along the edge of the mucosa, okay? And what we need for every molecule that's in the solution up here to eventually, before it passes through the whole small intestine, to get in the position to be right up against the mucosa so that it can be absorbed, okay? And so we do that. I think I did something bad there. Here we go. So we have a lot of these movements that go on in the wall of from our intestine. There, it squeezes here and squeezes there and kind of pushes things down, as in peristalsis. But also, it just does a lot of mixing, where this squeezes, that squeezes, then this squeezes, then that squeezes. The whole idea is just to keep this stuff moving back and forth so that all of it eventually gets laying right up against the edge. And if it didn't move around a lot, the stuff that was laying right here would get absorbed, but the stuff that was laying right behind it would never get in touch with the mucosa, so that wouldn't get absorbed. But we have all of these movements of the intestine that make that happen, and these movements of the mucosa increase the absorptive effectiveness, basically just to get it all exposed to the mucosa. Let's talk about the colon for a minute, and the colon is, we talk about it a lot, but really it doesn't do much for us in terms of digestion. It does a little bit. What is the function of the colon? My teachers used to always tell me there's only 2 reasons to have a colon. One is to absorb the water back out of your colon, and the other one is to provide a socially acceptable method of holding onto your stool so that you can deposit it in a toilet every so often and not have it just dribbling out all the time. Now, if you were a rat, you just poop all the time. You see rat droplets, you know, they don't put them in piles, they don't store them any particular place. Whenever they feel like it, they just let it go. It's kind of like a fish pissing. Fish piss all the time, but nobody's sitting there pointing at them, you know, so they don't care. Well, that's basically the biggest function of your large intestine. Storage of fecal material prior to defecation. There are a few vitamins that are absorbed through the colon wall, and that's nice. But once again, it's a pretty minor function, actually. Let's talk about the large intestine for just a minute, and I'll draw a picture since I'm such a great artist, as you've learned. The small intestine comes down here, and it enters through the ileocecal valve, just a little muscular valve at the end of the small intestine, and it enters into the cecum. So this is the cecum. And hanging off of the cecum in humans is this little vermiform appendix. And then colon comes up, goes over, comes down, makes a big S turn, and then goes out. So, if I can run through this pretty quickly for you, I would just say that here's the cecum, and then this is the right colon, or called the ascending colon, because it's going up. And it comes up here to this corner right here, and we call that corner either the hepatic flexure, because the liver lives right there, or we call it the right colon flexure, either one. And then it turns into the transverse colon, which goes straight across. And then it comes to this corner over here, which is called either the splenic or the left colon flexure. And then it comes down, and this is the descending or the left colon. Okay? And then it reaches this area, and we call this the sigmoid colon because it looks shaped like an S. What a creative name. Sigmoid colon. And then the sigmoid colon turns into this last straight part, which is called the rectum. And remember that the rectum is retroperitoneal, so it doesn't have a peritoneal covering, doesn't have a serosa, it has a... You get to say it again. You love that word, I know you do. So anyway, there you go. The cecum is kind of pouch-like. The whole colon has a pretty thin wall. It's not near as thick as the small intestine in the wall itself. It is a little bit bigger around than the small intestine. I guess that's why we call it the large intestine. The cecum is the stuff that pours into the cecum down here in this corner is just pure water. There's nothing solid about it at all. You can't even, when you hold it up to a light, it's clear usually. There's very little suspended stuff in it. And it's going to take a number of hours or days to work its way around to your rectum. And that's going to depend entirely on how much fiber you have in your diet. Your bowel will move as long as it has something to move against. If it has fiber in there and there's something in there, it'll move. And so my dad was the ultimate nutcase when it came to his bowels. And, you know, he had to have a bowel movement every day, come hell or high water. He would go sit on the toilet until they moved. And sometimes that was a long time, which is really a bad idea. Because if you want to get hemorrhoids, just sit on a toilet. Because every minute you sit on a toilet, those veins that are around your rectum get swollen just from the pressure of everything, and especially if you're bearing down. Don't do that. Nobody should ever take a magazine to the toilet. You should go to the toilet when nature tells you it's time to go. Get on the toilet, try to get off in about a minute and a half, get rid of all of it, and get up and go. It's just not healthy to sit there.
She's visualizing, I think.
I know. It's amazing the things we talk about in here, isn't it? Yes?
Why do you, why does, like, all in general, that you call it restroom?
Why do we call it a restroom? Place to go rest?
If we can't sit there, why do
You
they
just
call it a
can't sit there.
squatty potty?
In the boys' bathroom, they have urinals, so they get to stand, right? Anyway, I don't know.
You need to get a squatty potty.
Yeah. So the appendix, also called the vermiform appendix. Vermiform means worm-like. You remember that little vermiform part of the cerebellum back there in the back of your head? Yeah, vermis. That's where that word comes from. It's normally about 9 centimeters long, so it's normally about this long. It has a bunch of lymphoid nodules in the wall of it, because we know that the appendix is basically there to fight infection. We don't know how it really does that because it's kind of hanging out to the side over here, you know. But that's what it's for. In chickens, if you're interested, chickens have a huge thing. It's called the bursa of fabricius. It's this great big pouch, huge thing, which is all lined with lymph nodes and lymphoid tissue. And it looks like chickens must really need that thing. We don't need it. The only thing appendixes do for human society is it sends surgeons' kids to college because you get called to take out appendixes relatively frequently. Anyway, I think that's all I need to say.
What causes the appendicitis?
What causes appendicitis? That's a very good question. Let's do a little close-up here. If this is your cecum, here's your ileum coming into it, and here's this long appendix. And along the wall of it here, there's all these nodules. They get they're lymphoid nodules, so they get swollen from time to time. And when they get swollen enough to block this off, now anything that's back here can't be drained, so it's going to develop an infection, and indeed that's what happens. The appendix starts to swell, and it starts to swell, and it starts to swell, and then it bursts. And that's a ruptured appendix, and then you've got basically stool and stuff dumped out into your abdomen, and that's not a very good thing. And just so you all know, from a historical point of view, this fascinates me. The first time that appendicitis was ever described as a disease